All right, we're going to talk about function composition today. And this notation here is F composed with G. So it's just a little circle there. It's not the letter O. It's a little circle between F and G there. F composed with G is taking the G of X function, or whatever's written second, and putting it in for X in the F of X function, is what that function composition is. And then we'll talk about the domain of that because it's function. We talk about domain of functions in every section of every chapter of this book. So it's a set of all numbers x in the domain of g of x, whatever your second function is, such that g of x is in the domain of f of x. So when it says g of x, we're talking about the y values of that function in the domain, the x values of f of x, first function. And I think you start making a little bit more sense when we start doing a few problems with this and actually doing that composition and finding the domain of that. But it's not, it's kind of wordy when you look at it as a definition, but it's not as bad as it looks when you actually start doing the math with it. It's not too bad. So let's just look at our first example. F of x, 2x squared minus 3, and then g of x, make it pretty simple, just 4x. Okay, so we want to find f composed of g of x and state the domain. So one of the things you want to do here is find the domain of f of x, and then also find the domain of g of x. And then we're going to use those to find the domain of that composite function. And then we'll actually find the composite function. So looking at those two functions up here, are there any restrictions, any red flags that are happening on those? So what would the domain of f of x be? All real numbers, so negative infinity to positive infinity. What about g of x? Yeah, negative infinity to positive infinity. Still the same. Now, if there are no restrictions on either one, would there be any restrictions on the composition of those two? Couldn't be, okay? If there aren't any restrictions on either function, your domain of f composed with g of x would be from negative infinity to positive infinity. So that's pretty easy. That wasn't too bad. Pretty easy one to start with anyway. Now let's actually find that composition. F composed with g of x. The thing to remember is that it's the second function into the first one. Okay? So you're taking, bless you, g of x and putting it into the f of x function in the place of x. So that means you're taking 2 and then putting 4x in the place of x. Minus 3. And then you just want to simplify that. So that when you're doing the composition, you get that composite function is what it's called. And you simplify it as much as possible there. So we're going to simplify that. That'd be 2 times 16x squared. Which would be 32x squared minus 3. And there's our function composition, or our composite function. 32x squared minus 3. Pretty easy on that one because there weren't any fractions involved or no restrictions on the domain there. So it's not a extremely difficult thing. All right. Let's look at a little bit more interesting. Let's get f of x is 1 over x plus 5, and g of x is 4 over x minus 1. And again, we're going to do the same thing. We're going to find the composition and its domain out of that. Okay. So, are there red flags on either of those original functions? Both of them. Both of them have an x in the denominator, so that tells us that we've got some issues to deal with. What's the domain of f of x? Yeah, so x can't be -5. We're going to take the shorthand version on the two smaller functions, and we'll do the interval on the actual composite function, the actual thing we're actually trying to find. What's the domain g of x? X can't be +1. Good job. All right, now, here's what we've got to find. Because we have restrictions, we need to know when is g of x equal to -5. Because remember, we're doing the function composition, f composed with g. You're replacing x in the f function with the whole g of x function. So g of x, that whole function, is now the x part of f of x. So we need to know when that's happening. So g of x was 4 over x minus 1. When is that equal to -5? So this is similar to what we were doing in the last chapter when we were talking about crossing the x-axis, or crossing the asymptote of a rational function. So we can solve this. We know how. How do you solve that? Multiply each side by x minus 1. 4 is equal to -5x plus 5. Subtract 5. -1 is equal to -5x. X is equal to 1/5. Okay. Now, the composition. A bit more difficult on this one because you got fractions involved, but we're taking the f of x function, 1 over x plus 5, and we're adding, instead of x, we're putting 4 over x minus 1 in its place. So we've got to think about adding and subtracting rational expressions. If we're adding, subtracting fractions, what do they have to have? The denominator the same. So the denominator on this fraction is x minus 1. So this one has a denominator of what? 1. It needs to be x minus 1. So we would multiply top and bottom by x minus 1 to get that the same. So that's 1 over 4 over x minus 1 plus 5x minus 5 over x minus 1. Not going to get too complicated with these rational expressions here. That it should be fairly small amount of work to get a common denominator and work with those. And there won't be this on every problem either. It just depends on what you're given. Okay, and then you just simplify as much as possible. On the bottom, we're going to have 4 plus -5 be -1. So that's 5x minus 1 over x minus 1. Fraction inside of a fraction is a no-no, right? You can't have that. So dividing by a fraction is the same thing as doing what? Multiplying by its reciprocal. So the reciprocal of the denominator is, and since we're multiplying by 1, that's all that's there. F composed with g x. There's our composite function is x minus 1 over 5x minus 1.
How did you do that?
This?
Yeah.
4 plus -5, -1. and then plus a 5x. And the denominator doesn't change any when you add subtract fractions. So as long as it's the same on each fraction, the denominator stays the same. Okay. All right. Last thing is the domain of that. Okay, because we had restrictions here on the domains of each individual piece. We need restrictions on the domain of the composite function. So domain of f composed g of x. All right, so let's look at where it came from. We know x cannot be what for g of x? Well, that's for f of x, the negative 5 is. For g of x. It can't be 1, and then for the composite part, can't be 1/5. Now, the negative 5 really doesn't matter. Okay? Because we've replaced the x in the first function, in the f of x function. Remember, in the composite, that's what got replaced, was the x in the f of x function. We had to deal with it to find that restriction, but there's this restriction there. So our domain for this would be x does not equal 1/5 or 1. And then let's get the interval notation for that. It would be negative infinity to 1/5, 1/5 to 1, 1 to infinity. There would be our domain. The piece that we found for the first function, what's listed first in the composite, it's used, but it's not part of your final domain. That's one thing that you can kind of remember out of it. Because if there's a restriction on the first piece, you use it, or the first function, you use it, but you don't list it in the composite functions domain. Just if you can remember that, that'll help you kind of weed out some of the things that you got to do here. All right. Let's look at another one. F of x, square root, x plus 3, g of x, 2x plus 5. And again, we're going to find the domain and then do the composite function of that too. Same instructions, not doing anything different here, just kind of running through this same idea.
Is that what we're going to be doing for every problem in this section?
Not necessarily the whole thing for every problem. You may, and you may be asked to find a function value of the composite function, like f composed of g of 4. Well, you just find the composite function and then plug 4 in for x at the end. So it's not always this difficult as this is. You're not always going to be doing the whole thing. We're just doing the whole thing here. All right, so let's get domain stuff going. So domain of f of x. Any restrictions? Yeah? How do we find the restrictions for f of x? X plus 3. Is it just greater than or equal to? I heard both. Equal to, because we can take the square root of 0, right? So that's why the equal to mark is there. If that were in a denominator, then you would drop the equal to part. But if it's just straight up square root, there. So x has got to be greater than or equal to -3. Any restrictions on the domain of g of x? It's negative infinity. Positive. Why does it do this during first block and not the rest of the day? I don't understand it. All right, so we have a restriction on the f of x function. Remember, when we're doing function composition, the second function that's listed is the one that's going into that one. So we've got to know when is g of x fitting this domain. So when is g of x greater than or equal to -3. That's what we got to know for the composite function. So you got to take your second one, think about the domain restriction from the first one. And so we're setting 2x plus 5 greater than or equal to -3. And solve. Not plus 5, it's minus 5. 2x is greater than or equal to -8. X is greater than or equal to -4. Okay. Then let's go ahead and find that the composition of those two functions. F composed with g of x. So inside of the f of x function, we're replacing x with the g of x function. So instead of x plus 3, it's 2x plus 5 plus 3. And in like terms, so that'd be 2x plus 8. So there's our composition or our composite function. The domain of the composite function. We've actually already found it. X has got to be greater than or equal to -4. That was from that question right there. That's where that came from. Okay. So for the domain of the composite function, you've got any restrictions that are from the second function listed, and the restrictions for when you set the second function, whatever, to the domain of the first function. That's what the composite function's domain is going to be. So interval notation, here's set notation. Interval notation would be from -4 to infinity with a bracket on it. Notice that the f of x function, the first function that's listed, its domain really doesn't matter at the end here. Look at the composite function. How would you find the domain of it? If it was given to you just as an original function, like chapter 3, find the domain of that 2x, the square root of 2x plus 8. What would you do with it? Set it greater than or equal to 0. When you do that, what do you get? You get x has to be greater than or equal to -4, the same thing that's here. So we can find that domain from the composite function, especially when it simplifies a lot. But we could lose some pieces if it's a fraction. You notice on the previous problem, we had those fractions. Look at the composite function. The only thing we see if we set it equal to the bottom equal to 0 is the 1/5 part. We would miss the 1 part that's here if we just did that. So you've got to look at the domain of both of them, of both individual functions, and then that builds your composite function, its domain. All right, so let's take example D, and let's say that good. Let's take the same two functions. F of x is equal to the square root of x plus 3, and g of x is equal to 2x plus 5. And then let's do, okay, you got it? Okay. I want to run off further. And let's do the other direction. Let's find g composed with f of x and its domain. Okay? So we're going in the other direction. Now we're replacing x in the g of x function with this square root stuff. Okay? So I think this will help us understand that, hey, the second one's the one that really has it's doing all the work here. Okay? So domain g of x. What's the domain of g of x? Yeah, negative infinity to positive infinity. All real numbers. Domain f of x. Is it not equal to, or is it something else? Greater than or equal to. X is greater than or equal to -3. Because you're setting whatever's underneath the square root greater than or equal to that. All right, so we get x is greater than or equal to -3. This is the one that matters. There are no restrictions on the first one. If there are no restrictions on the first one, we don't have to do another problem to work anything out, because all we've got is f of x is greater than or equal to -3. We don't have anything to decide about on this one because there's no restrictions. Okay? The second one is the one that decides, do we need to? If there are restrictions here, we would say, okay, well, when does f of x equal whatever the problems are? Okay, but we don't have that problem with this one. Okay, so let's find the composite function, and then we'll get the domain of it. Okay, so we're taking g of x. I wrote it backwards. Sorry. G composed with f. That's the one we're doing. We've already done the other one. We don't need to do it again. So g composed with f. So we're taking f of x and placing it into g of x. Okay. 2 parentheses radical x plus 3 plus 5. Not really anything you can do to that. There's our composite function.
You're always looking to find a component.
If it asks for it, yes. And then domain of g composed with f of x. What's the only restriction that we had? Yeah, x has got to be greater than or equal to -3. Look at the composite function. That's the only red flag that exists in there, right? That should match up with what your domain is. So our domain would be x is greater than or equal to -3, or -3 to infinity. Those are our domains for the composite function.
You just put the bracket because you've already found the domain of g of x and positive.
The bracket is because of the equal to sign here. But this says x is greater than or equal to -3. If I had a parentheses right here, it'd just be greater than -3. It wouldn't include the -3. Let's do another one, see if we can maybe get a better understanding. H of x is equal to x squared plus 5x plus 7. Make that a minus 5x. Not that it really matters, but just so I'm consistent with my notes here. 3x over x minus 2. Let's find h composed with k of x and the domain. Okay, so using h and k and just changing up letters to them. So, first thing we want to look at is the domain of each individual function. Okay. The first function, does it have any restrictions? So its domain is all real numbers, right? Negative infinity to positive infinity. And then k of x has what as a restriction on the domain? Can equal 2. Good. Okay. So if the first one has no restrictions, do we need to do any more work? The answer to that is no. Because there's nothing in the first function that's going to mess up the composition. If there are restrictions on the first function, like here it's asking for h composed with k. If there are restrictions on the h, yeah, when the second one works with, has that as a domain. That's right, Dylan. Good job. So if there are restrictions on this, then you've got to find when does k of x do that. Okay, when does that happen with the second function? Since there's no restrictions on the first function, you don't have to do that. You can skip on to do the composite function. Okay. And we should see that the composite function should have a domain matching the second function, is what we should see. Let's do the composite function, f composed with k. X. So what are we doing for h composed with k? Everywhere there's an x, we're putting what? 3x over x minus 2. Okay. Mm, 15x. Not really going to get much better looking from here. But let's go ahead and,
Why didn't you do 5 with x minus 2?
because it's 5 over 1, it's a fraction. So top times top, bottom times top. All right, so what would the common denominator for those three be? Just x minus 2? Should be squared, right? Because this one has 2 of those x minus 2s. This only has 1. So it's kind of like if 49 was under 1 and 7 was under another, the common, you'd use the bigger one there. So we need x minus 2 squared. So the second fraction needs another x minus 2. That third thing that's not even a fraction yet needs both of them. It needs x minus 2 squared. So that's x minus 2 squared written out there to the side, kind of squeezing it in there. Give myself a room here, 9x squared. And then the bottom part's going to be x minus 2 squared. That's the bottom part. So the top part, we're just working this out. 15x, negative 15x times x minus 2 would be negative 15x squared plus 30x. And then this one, x minus 2 squared is x squared minus 4x plus 4. And then distribute a 7 to that. So that's 7x squared minus 28x plus 28. So that's coming from 7 times x minus 2 times x minus 2. That's x squared minus 4x plus 4 times 7. That's this part. That's where that's coming from. I just did that in my head. Do it off on the side or somewhere. And then you're just simplifying the numerator there. The denominator is not really going to do anything. The numerator needs to be simplified. So 9 minus 15 be negative 6. Plus 7 be 1x squared. Then we have 30x minus 28x would be 2x. And then plus 28 over x minus 2 squared. So there's our composite function. It simplifies down to look pretty decent as far as that goes. But now the domain of that. What's the only restriction that exists? X has got to be anything but 2, right? Negative infinity to 2 to infinity. All right, not too bad. Not too bad. Let's do one more. What letter we on? F. F of x is equal to x squared minus 5x plus 7. G of x is equal to 3x over x minus 2. Let's find G composed with F of x and so what's the domain of the first function? G of x. G of x?
No,
X cannot equal 2. Domain of the second function. Yeah, so it's negative infinity, positive infinity. I do it in the order that it's listed here. No matter how they're listed as, given to you in the original problem, the way that the composite function is listed is the order that I do them in. That keeps me thinking, okay, restrictions on the first one, restrictions on the second one. That helps me, keep that in mind as I go. Okay, so no restrictions on the second one, but there are restrictions on the first one. So what do we have to do? Yeah, well, not equal to 0, but equal to 2. So we need to know when is f of x equal to 2. We're having to do that because the first function that's in the composite function has a restriction. Okay, so x squared minus 5x plus 7 equals 2. It's a quadratic, so how do we solve it? Get it equal to 0, so subtract 2. That's x squared minus 5x plus 5. And then what are our options? Factoring doesn't work. There's nothing multiplies to be 5 and adds to be negative 5. Quadratic formula for that would be the way that I would go about that. Negative b plus minus radical b squared minus 4ac, so negative 5 squared minus 4 times 1 times 5 over 2a. So that's 5 plus or minus the square root of 5, because 5 squared is 25 minus 20 is what that multiplies to be. So the discriminant is 5. Does that simplify any? No. So x can't be those two numbers. So that's going to be the domain of our composite function, is that x can't be those two numbers, because that's the only restrictions that matter. Remember, the restrictions on the first function listed in the composite function don't really matter when it comes to the actual domain of the composite function. It's all about the second one and then the application of the second one. Okay, so let's find that composite function. This one's a little easier because you don't have to deal with the fraction as much. So we've got G composed with f of x. So everywhere there is an x in the g of x function, we're placing a f of x stuff. So that's 3 times x squared minus 5x plus 7 over x squared minus 5x plus 7 minus 2. Simplify as much as possible. So that's 3x squared minus 15x plus 21 over x squared minus 5x plus 5. That should be familiar. We've seen that denominator already. We were talking about the domains. And there's our composition function. Domain. X can't be, we already know what it is. We've already done the work. Now for the interval notation of that, it's a little bit more difficult, but it's negative infinity up to the smallest one, which would be the subtraction one, 5 minus the square root of 5 over 2. And then from that to the plus one. And then from that, give myself enough room here. Move it to 5 plus the square root of 5 to infinity. There would be the domain.
So you move that, you added 2 into the parentheses in the blue?
Yeah, like current. Right here, 7 minus 2. So that's where this plus 5 came from. So just simplifying there. And I just distributed the 3 on top. Not that it did any good, but it looked like some unfinished business that needed to be taken care of there. All right. Not horrible stuff, but the key is to remember which function in the composite function really carries the most strength. The second one. The first one doesn't do as much. It's important, but it doesn't have as much punch power as the second one does. Okay? The second one really has to do a lot, and it's got some restrictions on it. So practice problems. We got about 30 minutes left in class today. If you want to get started on it, I suggest maybe doing a little bit just so you get better at it. Page 404, 9 through 44, and then 67 through 70. Skip a few there. Some things that we don't cover out of this section. And I'm not asking you to do. And then work day tomorrow, and then quiz Wednesday. And there will be a couple of double sections this chapter and next chapter. But we'll do 2 sections together because they really relate to one another. So that you won't have you won't have 8 quizzes for chapter 6. You'll have less than that. And so we'll kind of see how that goes between now and spring break. We got this week and next week. And spring break. Anyway, all right. I'm done.